Hi, Assalamualaikum to all and greeting to my panels. My name is Muhammad Haziq bin Muhammad Shamsuddin and my metric number is B0919104588, and I will present to you about my project, which is biodegradable packaging from wood dust environment properties. Before that, my supervisor is Dr. Ridhwan bin JUMAIDIN. For the background, bioplastics are becoming a feasible replacement for conventional plastic and their applications. Thermoplastic starch has gained considerable attention recently due to its thermoplastic-like processability using plasticizer under high temperature and shear. Its properties are greatly influenced by production parameter plasticizer concentration. The selection of wood species for use in wood dust reinforced polymer composite may have a significant impact on composite microstructure and behavior. For the problem statement, it is because of environmental issue by plastic pollution. We all know that plastic takes years, hundreds of years to decompose. And next, a limitation of thermoplastic starch and waste of wood dust that we didn't do nothing about wood dust. So for the adjective, to prepare a biodegradable thermoplastic cassava starch reinforced with wood dust fiber composite, then to evaluate the environmental properties of biodegradable thermoplastic cassava starch reinforced with wood dust fiber composite, and lastly, to fabricate the biodegradable packaging derived from wood dust fiber and cassava starch. The scope of study and limitation. The outcome of recent study might deliver a new information regarding to the biodegradable thermoplastic cassava starch reinforced with wood dust fiber composite. The problem related to the environmental pollution might be reduced by applying the fully biocomposite material started with wood dust fiber and thermoplastic cassava starch. The problem by conventional thermoplastic also can be diminished by introducing the new material from cassava starch. More value added to existence of wood fiber and cassava starch using as its new reinforcement material by producing biocomposite product. Okay. So we go to the literature review. As for the starch, starch consists of amylose and amylopectin, and starch is utilized extensively in non-food industries for a variety of use. Starch not only used in food industry but also used in non-food industry. Then starch is soluble in cold water, alcohol, and other solvents. Next is thermoplastic starch, or TPS. The polymer source employed in manufacturing of biodegradable plastic are amylose and amylopectin. TPS, or thermoplastic starch, is made by applying mechanical and thermal energy onto the starch granule by adding plasticizer. Okay, so this is the application of starch. Okay, as you can see, there's a type of starch for cassava, corn, and sugar palm. So the potential application for cassava, it can be a biodegradable polymer, biodegradable material, food packaging plastic. As for the corn, we can use as a green material for packaging, hybrid biocomposite, and bio-based composite. For the sugar palm, it can be a bio-based polymer, bio-nanocomposite material, food packaging, and hybrid biocomposite. So for the wood dust, biodegradable and recyclable material that is used in production of polymer-based composite. It produces a pulp with short fiber that is excellent for tissue and writing paper as part of the finish. Wood dust is mostly constituted of cellulose 40 to 50%, polyoses, lignin, and a vast and variable number of smaller relative molecular mass compounds. So for the glycerol is a solvent used in production of food flavor and color. It is a colorless, sweet tasting, odorless, and viscous liquid which with a low toxicity that is widely used in pharmaceutical formulation. Glycerol contains 3 hydrophilic alcoholic hydroxyl group which contribute to its water-soluble and hydroscopic properties. So this table shows properties when the glycerol at 20.1 Celsius. As you can see, the molecular weight is 92.09 and the melting point is at 18.17. So as for the boiling point is 290 degrees Celsius. The density is 1.261 and then the vapor pressure, viscosity, specific heat, thermal conductivity, and also the effective index. So next is palm wax. Palm wax is made by a Capanesia cerifera martis palm, also known as carnauba wax palm. So it raises the melting point of gel, making it a popular ingredient in lipstick, lip balm, and mascara. Self-emulsing mixture of alcohol emulsion and palm wax may form solvent-resistant superhydrophobic coating, and palm wax is used to harden other wax and increase the melting temperature of wax mixture. So next, I will tell you about the methodology for my project. So this is the research methodology in flowchart diagram. As you can see, we start with a raw material selection, then we divide it into the wood dust fiber, which has a percentage 10 to 50%. Then another one is we make a mixture of cassava starch, glycerol, and palm wax to make TBCS with thermoplastic cassava starch, and then either we have to make a 0% fiber to put them in the hot press, or just make with a mixture of wood dust, then we hot press it. Then after the sample has been made analysis, where I divided into 3 analyses, which is water affinity analysis, physical analysis, and environmental analysis. These are the material that I've been used to create the thermoplastic cassava starch with wood dust fiber. First we have the wood dust fiber, then we have a cassava starch, palm wax, and also a glycerol. So these are the preparation of thermoplastic cassava starch reinforced with wood dust. So first we have to weight cassava starch, then weight the glycerol, weight palm wax, weight the wood dust with a specific weight, then we weight the mixture and then blend. So after we blend, we compact the mixture into the mold that has been made. Later, we place it in the hot press machine for 50 minutes. After 50 minutes, we remove the mold to take the sample out. So I will explain about the water affinity testing. So the testing that I will make is a moisture content. We only use a electronic weight scale as the apparatus. Then for the calculation, I only take the percentage of moisture content, which only I will minus the weight of beef after minus weight after, then weight before, then divided by the weight before, then we multiply it with 100% to take the percentage. Then the next testing will be water absorption. Also use the electronic weighting scale, and the calculation also same with which is I only take the percentage with same calculation. Then I will take thickness swelling, but the practice I will only use the vernier caliper. Also the calculation I will use the same calculation uh, to take the percentage. As for the environmental analysis, there's two tests that I will make. That is water solubility and salt burial. So the water solubility, I will use the electronic weighting scale as the apparatus, and also the calculation also the same, which I will take the percentage of weight reduction. And as for the salt burial, I will use the electronic weighting scale, and I will also take the percentage of weight reduction. So next is a physical analysis. So as for the physical analysis, also I will make two tests, which is FTIR, Fourier transform infrared spectroscopy, and SEM, scanning electron microscopy. So as for the FTIR, I will use the JETSCO FT, this one spectrometer, and then for the SEM, this is EVO 18 scanning electron microscope. So this is the preliminary result that I made for in PSM1. So I only made the moisture content. So this is the result. As you can see, the pure TPS sample has the highest moisture content. So this is the result. It has about more than 8% moisture content in the zero percent without fiber, which is it doesn't have any fiber. And then then the moisture content data indicate the cellulose fiber has a greater property to absorb atmospheric moisture. So this is based on the Gobikanan, that the journal that I've been beside. So based on my result, you can see that the percentage is dropped. The moisture content, the more I use the fiber, so the moisture content is dropped. Okay, next is the other testing. So the other testing that I will continue in PSM2. So I will explain the expected result for it. So as for the water exertion, that is insertion of WDF into the TPCS metric would significantly minimize the water exertion of the TPCS metric and water sensitivity of the TPCS. So this is according to the Piachawa-Racon. Water exertion might significantly lower the thermoplastic metric water exertion and the fiber water sensitivity. So next, for the thickness swelling, the expected result will be with the rising pump wet concentration. The predicted outcome of this investigation is a considerably drop, and a lower swelling index is preferred for a variety of applications due to its indication of enhanced water resistance. Uh, then for the water solubility, due to the hydrophobic qualities of palm wax, the addition of palm wax improved the water resistance of the biocomposite. It was discovered that palm wax not only lowered water solubility but also maintained the structural integrity of sample when submerged in water. So as for the FTIR, it is expected to show the chemical bonding characteristic of a material composite, in this example between fiber and starch. For the SEM, which is scanning electron microscopy, this test is expected to show clearly that the fiber were very well dispersed in starch metric. So this result is based on Cervelo in his research 2001. So this is all from me for my project PSM1 presentation. Thank you for listening to my presentation, and Assalamualaikum.